Okay, I'll be taking this in English, since all words are in English. So I'm talking about generative adversarial networks, what they are, and how they work, and could they possibly be the future of deep learning? But first, I have a short question. You seen any of these people before? Chances are you don't, as all of these images are generated. These are not real people. But how are they generated, and what are generative adversarial networks? So in order to answer this question, we first need to know the difference between a discriminative network and a generative network. So what you usually think of when you talk about neural networks, that's a discriminative network. It's a network where you send in a bunch of features or an image, and you try to classify this image by putting a label on it. So an example could be you have a bunch of images containing numbers, and want to know which number is in a given image, or a dog or a cat, hot dog, not hot dog, so forth. Well, the generator, or a generative network, does the opposite. We give it noise, random values, and it generates a set of features for you. So in the case of an image, it would generate an image which looks like other images it has seen before. So now to know what a generator is, a generative network, we should look at the next word, which is adversarial. This comes from adversarial examples, which are features or input images that have been purposely adjusted or modified in order to fool a discriminative network. So here we have an example. You have the first image, which is classified as a panda. Then you adjust some of the pixel values, and the result still looks like panda to us, but to the network it looks like a gibbon with a 99% confidence. So now we know the basics. Let's look at an example. Down here we have our generator. It takes in some noise and generates a set of fake images. And then, in addition, we have a set of real images, which we want the generator to the fake images are supposed to look like real images. And finally, we have a discriminator, which is just a usual neural network, which is trying to differentiate between real and fake images. But the thing is, it doesn't know, because the images it can see in are mixed, so it can't really know which if an image is real or fake. It has to learn it. And by generating images and putting them through the discriminator, you can train both the discriminator and the generator at the same time. And then, when you're finished, you have a satisfactory result. You can only look at the generator, which then will be able to generate an unlimited number of different images. So a more abstract example could be that you want to draw like Picasso. You want to make Picasso art. But you have never seen Picasso art before. So you just take out a piece of paper and you start drawing. You draw a bunch of images which you think look like Picasso's, and then take them to a friend who hasn't seen Picasso's art either, and you give him a bunch of real Picasso art pieces, and maybe not the real ones, but images. Then give him these together with your fakes, and then he has to differentiate. And after it's done, you tell him the truth, which images are real, which are fake. He learns a bit, and you learn by looking at him trying to differentiate between real and fake images. And then you can repeat this process several times, and hopefully you get better at drawing, and your friend would get better at discriminating between real and fake images, until you get to a point where your images look like the ones of Picasso. That's at least the optimal end. So now that you know the basics, know what a generative network is, you can look at some different types. The first one is DC GAN, also known as it's a deep convolutional GAN. And essentially the only difference is it uses convolutional layers, which work really well for image processing. Anything with images, you just put in convolution and it works. And it's essentially the baseline for all generators which generate images. So yeah, every network that generates images has some form of convolution included. So another network, which is really cool, is the stacked GAN. And in this example, it takes in a text, and it generates a bird which resembles the text. For first image, we have a blue and white bird with a short beak. When we look at the final image, it indeed looks like, it resembles at least, a bird with a short beak. The way these images are generated are by what they call stages. They have 2 stages. In the first stage, they create a base image. They create the basic colors, the basic shapes. And then in the second stage, they further enhance this base image. They scale up the resolution. They create the final bird, the bottom row. And another example, other type of network, the InfoGAN. Because when you generate images, usually you only put in noise, put in random values. You can generate a wide area of different results, but you have a little control over what you're generating. So the team that created this network tried to solve it by, in addition to noise, giving the generator a latent code. By doing this, they were able to control the resulting images. So in this example, they tried to generate chairs, and the latent code they used was the width of the chair. So it's going from left to right, from width to narrow. You can see all images still look like chairs, but they're getting smaller and smaller. So I have even more examples. One is the amnesty dataset, which is really often used. It was the first I tried when attempting to create a generative network. It's just pictures, 28 by 28 pixels, really small, of numbers from 0 up to 9. And here you can see the result during the training process. You can see at the start it's just random noise, just gray images, but really fast they start to resemble real numbers. You can also see some of the numbers changing from 0 to 6, from 8 to 0. So they're really similar, and you can see the similarities between different numbers. Here we have yet another set of examples. This one's from the same as the celebrities in the first image, the same network created by NVIDIA. And all of these images, at first look, they look just like normal images. It's really hard to distinguish. Like the sofas could just be from the IKEA catalog. But if you look closer, you see like a horse with 2 heads. Not sure if it's usual, but also the bikes, they look like bikes, but if you look close, the wheels are kind of wobbly. So But all in all, they really look like real images, and it's hard to distinguish between these and actual images, which is what we can do here. We have one fake image amongst all of these dog images. And you know which it is?
Bottom left.
No, it's the top right. This is from a network called Big GAN, in which they try to create images with as high a resolution as possible. I think these images are 500 by 500 pixels. And yeah, it's really hard to distinguish the actual fake image from the real ones. Here's another cool example I found. In this network, instead of sending in noise, they send in an image, and then they train the network to generate a matching item. So in the top example, they send in handbags, and they make the network generate matching shoes. In the bottom, do the opposite. They send in shoes and make matching handbags for your shoes. Here we have yet another example. One of the images is fake, the others are real.
Top second.
It's the top, the right. Yeah, it's really hard to distinguish the fake image from the real ones. What they've done in this example is they've used the fake image to find the similar images within the dataset. So you can see even it's not overfitting, it's creating its own image, but it looks really similar to the images from the dataset. So you might think, oh, this is cool. Why don't we see it everywhere? And of course, these networks come with a bunch of problems. Because if you think back at our example, if you were drawing Picasso and your friend would say, would be fooled every time, how would you know that your friend's just not bad at guessing? If he's blind, how would you know? There are several issues. One of them being non-convergence, that the parameters, they just continue and never converge until a final value. This is because you're essentially letting the generator and the discriminator fight against each other. So if the generator does good, the discriminator does worse. So they will always try to compete with each other. And another issue is what they call mode collapse. This can be seen in this image from the amnesty dataset. The top is what it should look like. The bottom is what it looks like. And the issue is that your network, instead of creating the entire spectrum of possible images, it finds one where it can fool the generator, and it just continues creating this one image. And when I tried this, I had the same problem. My network would only create ones. Was really good at creating the number 1, but didn't create any of the other numbers. The third issue is diminished gradients, which happens quite a lot. That's when your discriminator is so good that your generator is not able to learn anything. And a solution could be to just dumb down your discriminator, give it fewer layers. But then again, you wouldn't reach your optimal network structure. The fourth issue is that these networks are highly sensitive to hyperparameters. So just adjusting the learning rate a little bit, giving it a few more layers, adjusting layer sizes, everything matters. And it's really hard to get the network to converge on the final value. So to sum up, there's a really high potential here. The images, if it works really good. But getting to that point is really hard. And it's still highly experimental. And it's hard to balance the discriminator against the generator without doing some form of cheating, dumbing one down, giving it a lower learning rate. And it's really hard to know during training how you're doing. Are you doing good? Are you doing bad? You don't know. But it's getting better. NVIDIA is doing amazing progress with these images. And overall, the computing size, amount of computing power is increasing. So it's steadily getting better. But it's still at a very experimental stage. And it's really hard to get it up and working in the first try. That's all I have for today. Questions?
How do you update the generator? Like with the discriminative network, it's like you have a right and a wrong answer, right? And then you update the weights based on, how much they contributed to the wrong answer, right? But how do you do that with generators?
Generator does the opposite. So it's still connected, even though you take out the images in the middle, it's still just one network.
Okay.
So you can still feed the gradients backwards and just have the opposite goal. But it's of course it's hard because the gradients vanish the further up in the network you come. So it's hard to balance the training of the generator and the training of the discriminator at the same time.
Okay. So you update the generator based on what contributed to the discriminator getting the right answer.
No, getting the wrong answer. If it gets the wrong answer, the generator has done something right.
Yes, but if it gets the right answer, then you have then the generator's got to do better, right?
Yeah.
Yeah.
That's the basic.
Cool.